The New Future of Making on Mars, a tutorial conference for students. Discover possibilities for you to take part in the exploration of Mars. 5 tutorials, 1 plan for building a science station on Mars, 1 veteran's guess about the future, 1 super interview on hot robotics in Leo, 1 conference summary, and 8 subject matter world experts from NASA, top universities, and 3 space companies. Sponsored by the Mars Society of Canada and Maker Works of Ann Arbor. Organized by 2 Planet Steel. See possibilities you haven't seen before. In this talk, Searching for the Most Accessible Water Ice on Mars, speaker Roberto Aguilar takes us on a tour of how NASA-funded scientists hunt for Martian subsurface ice. He demonstrates how data from multiple spacecraft and instruments is sifted, decoded, and combined to reveal what's lurking beneath Mars's surface, especially with the SHARAD shallow radar instrument he personally uses. As part of the Subsurface Water Ice Mapping SWIM project, Aguilar explains how they have used radar profiles to dramatically expand our understanding of where we can find water ice on Mars. SWIM data is one of 2 water datasets being used for deciding on where to land the next generation of Mars spacecraft. To assist viewers, the meanings of some technical terms are given below in the video's description.
Okay, thank you so much for the introduction. So yeah, I'm a PhD candidate at the University of Arizona, and I'm also a member of the science team of SHARAD, which is sounder or a ground-penetrating radar orbiting Mars on board the Mars Reconnaissance orbiter, which is this spacecraft we have here. And yes, I will be speaking today about my work as part of my PhD and the tasks I do as part of a member of the science team of SHARAD, and also some results of SWIM. Okay, before I start with the methods and modeling and the remote sensing techniques that we have used to produce some mapping of the ice, I want to start off with the motivation for this work. Like, why do we want to search for accessible water ice on Mars? There are 3 main reasons I'm listing here. The first one is because they are targets for in situ resource utilization in case we would like to send humans to Mars and they would like to produce like fuel or use water for daily activities. We could reduce the amount of resources they should bring from Earth if we have the possibility to drill ice, utilize the water on Mars. Second, if there are locations where we could find for extinct life on Mars, are mid-latitude locations with water. And actually, there is a mission called the Mars Life Explorer that's targeting or has selected some sites at the mid-latitudes of Mars to core ice with the current technology of about 2 meters and search for some signatures of life in those areas. And the third one is, since we have the change in obliquity of the planet, we had multiple episodes of glaciation. So if we could detect the multiple, like different layers of debris and ice, we could also get some hints about the records, some records of the past of Mars, just by searching for this mid-latitude ice. Okay, so these are just a figure with some a comparison between Earth and Mars. So Mars have a similar tilt as Earth does right now, which means that we also have seasons on Mars. The day it's around the same, like 24 hours. The year is longer on Mars, but there are some main differences. First, Mars is colder, and also the pressure is lower than we have on Earth. On Mars, we have polar ice. And if we are looking for accessible water ice, yes, the caps would be a very accessible location because the ice is right there. We could just go and we don't have to drill through debris or anything. It will be right there. But there are some problems with that. Temperatures are very extreme. The terrain is challenging, and also during winter, either south or North Pole, the nights are very long, which means we'll have problems with energy and communications in case we send like crewed missions or even robotic missions to these latitudes. At the mid-latitudes, at least from this figure of Mars, we have at the top right of our screen, there is no visible ice. But if we see this map I have in the middle, there has been some ice buried under a layer of debris that it's very like it's not like constant the thickness, or maybe it's not very pure in all the locations, but at least we have a map or where potentially we have water ice. Okay, to show an example how that mid-latitude ice looked or how the buried ice looks, I will show some examples on Earth. So here we have two debris-covered glaciers, one on Mars, one on Earth. Both of them we have evidence of viscous flow, which means at some point there was some ice accumulation at the top of this glacier, then the ice was flowing, and at some point, maybe after a few episodes of accumulation, there was a debris deposition. So what this means that, okay, maybe on Mars, these glaciers are not evolving because we don't have any snowfall or any debris deposition, but on Earth, we can go to the field to these study sites or terrestrial analogs and actually measure and understand how they are evolving, how they are changing, and what the interior of them look like. Also, on both planets, we have observed some outcrops of ice underneath a layer of debris or a layer or dust. So, for example, on the left, we have an example taken by HiRISE. It's a camera also on board the Mars Reconnaissance orbiter, where it observed, I think it's a few hundred meters of ice on top of a layer of debris. And on Earth, we have an example on, actually, it's a very dry place, as Mars is, here in the Atacama, where we have a layer of debris covering a thick layer of ice. And also we have some multiple layers that also provide some information about how these glaciers form. Okay, and here I wanted to provide an example of also part of my work when we want to study this debris covered ice. We can go to terrestrial analogs and actually, like we have in the figure of the left, we can go and measure the debris manually and then see that actually we have thick ice or a very clean ice. Then in the middle, we have an example of some of the techniques we have been using, that is ground penetrating radar or GPR. And we could do that manually, but if we wanted to do that on Mars, probably a drone solution like the one we saw in the previous presentation would be more suitable. And actually, we have been testing a drone-based ground penetrating radar in debris covered glaciers on Earth that help us first understand how these glaciers on Earth form and try to take some of those like knowledge and lessons to understand how they could have formed on Mars, and also try to develop and validate the ground penetrating radar and drone technology for future Mars missions. And this is one of the results. So here in this also terrestrial analog in Alaska, it's a debris covered glacier. We see here we have two radar profiles, one obtained with a drone-based GPR on the right, and on the left, and on the right we have a manual system that the one I showed in the previous slide, and we see that with both of them we can detect the surface. We can detect in the first arrows in magenta the debris ice interface, which means that we are detecting how thick that layer of debris is covering the ice, and also finally how we are detecting the base of those glaciers. Okay, on Mars, we don't have that possibility to go, at least at the moment, to go to the field, find a nice exposure, measure the debris thickness, check like visually with photos like how clean the ice is. So for that, we have been using some orbital missions. One of them is the Mars Global Surveyor, which was started operating in 1996, and from that we obtained elevation, which is the figure we have here on the top, the middle right, and also thermal inertia. Thermal inertia is a property that tells us how resistive a material is to the change in temperature. So, for example, here on the bottom right, we have areas in yellow and red that are rocky areas because rocks like let's say cool down slower, like when we have a transition from day to night, and heat up slower from night to day. And the dust, which are smaller particles, cool down faster from day to night and the other way around for night to day. So here we're getting some information about the properties of the surface. And then the Mars Odyssey not only scanned the surface, but also with the neutron spectrometer, we got some information about the first meter. So what was the likelihood to have some water ice, at least in that first few centimeters? And also we also got some thermal inertia data from this orbiter, which started working in 2001. And then with Mars Reconnaissance Orbiter, we not only have information about the surface or just the few first centimeters of the subsurface, we also have SHARAD, which is shallow radar. And as on Earth, as I presented the examples that we can see through the surface and see the ice, SHARAD let us do the same thing and see deep in the subsurface and image some glaciers. And this is an example of a 3D product generated with SHARAD radar profiles. And as we can see here, the first reflector that we see is the surface, so it's that bright reflector. But at some point, you will see that there are some internal layers that start showing underneath the surface. And those are the layers we can see with radar. We cannot observe that directly with like just a camera, because some of those reflectors are even up to a kilometer deep. But with radar, we can resolve all those layers of contrast between ice and debris, debris and ice, or maybe some pure ice in contrast with maybe some ice mixed with some dust particles. Okay, also, this is an example of how we have with missions that were not really originally just to study ice, provide us some information about what we observed with SHARAD. For example, the Phoenix lander, which landed, it was like mid-high latitudes. When it landed, exposed some ice. Well, at that area, SHARAD also detected some shallow ice that could be up to between 15 and 66 meters deep. This means that, yes, SHARAD is detecting the base of that ice, but we know there is ice in there because it was exposed by this mission when it landed, and the ice would be just maybe a few centimeters underneath that like very shallow, very thin layer of debris. Okay, SHARAD has also confirmed that the purity of some massive glaciers is pure ice. And this is an example of, on the left, of a figure of how a radar profile looks. So we have the first reflector in figure B is the surface, then the water ice, and then finally the base. And this is just a sketch of how we think those glaciers are, with the debris, a layer of debris on top, then some clean ice, and then some other layers of debris, and finally maybe all their ice underneath. With this, we can map these glaciers in 3D again and take some profiles. And interestingly, here in these areas, just by mapping these glaciers, we can see that we don't have just a very thin layer of debris. Actually, these glaciers, in this example, it's up to 700 meters of ice and very clean ice. And if we sum the ice containing these three glaciers, that could be comparable to the water we have in Lake Ontario. So we're not talking here about small amount of water. It's actually a big reservoir of water that is accessible under a thin layer of debris. Then, as part of SWIM, here I have been talking mostly about, okay, how we have this data gathered from different sensors. But how do we put this together? Okay, so SWIM was an initiative that wanted to find water ice, since it was identified as a critical resource. So, but before that, studies had focused on different instruments independently. So we had the neutron spectrometer in one side, then the elevation and difference study, or just high resolution imagery, or just radar. But with this study produced a consistency index And for example, it was like 3 different depths. So from 0 to 1 meters, it means like from just the surface up to 1 meter deep, we can use neutron spectrometer and thermal data. From 0 to 5 meters, we can use SHARAD returns. So just by the returns we get from the surface, we could also get, okay, what's the likelihood to have ice that, and finally, more than 20 meters, we can use the subsurface returns because we get a basal reflector of those glaciers. Okay, so this is one example of how we can go from neutron spectrometer data all the way to an ice consistency index. And the areas we have here on the right side in blue is the areas where it's more likely to have ice within the first meter, as this is the what we can resolve with this sensor. Also, this is like the 5 products generated in the last results of SWIM. So in the first figure, so if we go from A to E, the first one is the neutron spectrometer. So it's basically the first meter. So the areas in blue is where we likely have ice. Then thermal, again, blue is the areas where we could have ice. Radar surface, just by the surface return from radar data, how likely is to have ice on the surface, and then radar dielectric, this go more into the subsurface, and then finally geomorphic mapping. So just by looking at some images, we could delineate the areas where we would likely have some ice. What we do with this is at the end, we can average infrared composite of ice consistency across these 3 areas. So the areas in blue are the areas that is very likely to have ice, and maybe more like to white is where we could still have some ice, but it's less likely. Interestingly, in one of these areas here on this area that just popped up, there was an impact crater, and that crater was detected, and there was an image taken by HiRISE, and as we can see, that crater falls in an area that where SWIM detected that it was likely to have ice. And actually, first, HiRISE detected on the figure on the right that there was some ice exposed after the impact occurred, and also even the InSight, which is the seismometer, detected that impact. So again, by combining many of these sensors, and in this case, not only remote sensing, but also a seismometer, we could help us understand, like, okay, do we have those maps? Do we actually have a way to prove that there is ice in there? And as this impact crater demonstrated, there was some very accessible ice in that area. Yeah, this was a summary of SWIM. I just wanted to, before I move to some questions, if you go here to this website, swim.psi.edu, you will find some more information about the subsurface water ice mapping on Mars, which is SWIM. And if you hit NASA Mars Water Resource Maps, they will take you to this website where you could start playing with these maps and perhaps like change some of those layers. You could like pick like areas by elevation, and also like change the ice consistency maps. For example, if you want to check, okay, which areas will likely have ice in the first 0 to 1 meters, or from 1 to 5, or like below 5 meters, or we could just like combine all of them and get a more complete map of the areas where we'll have ice. So that would be my presentation. I will be happy to take any questions.
Okay, I'd just like to reinforce that this data is like really accessible. If you want to type into your search engine 2 things, SWIM, like swimming, and PSI, which stands for the Planetary Science Institute, which Roberto is closely associated with. And you get a great view of all of their data there. Easy to find. I have 1 or 2 questions. What do you see happening going forward in the next 2 or 3 years? Do you have any projects which don't depend on the Starship?
Okay. Well, something that we have been developing is the following. So SHARAD mostly have, so SHARAD is a spacecraft, and what we get is actually just 2D profiles. So we get a long track distance and depth. Something that we have been working on with the data we already have is create these 3D volumes. So we basically do a 3D migration. SHARAD has been targeting Mars for over 16 years. So what we're doing is combine all the data we have already available and make a volume. These volumes are very new. We started with the poles because we had more acquisitions there. Now, for example, my area of study specifically is Eastern Hellas, which is the southern hemisphere. And we created a volume there. We have also one for the northern mid-latitudes, and there are two in progress that are targeting also areas with very high chance to have water ice. So we could map that in higher detail. So that's what can I say for what can we do with the current data. There is a mission that it's planned. It's called the International Mars Ice Mapper. There are not any news on that at the moment, but that orbiter would operate at a different frequency of SHARAD. So SHARAD operates at a frequency of between 15 and 25 megahertz, which means that, yes, we can resolve 100 or more meters of ice, but we cannot resolve the first 5 meters. With IMEM, we will focus on those first 10, 20 meters of debris and finally resolve okay, how thick is that layer of debris, and provide more information about the places where we'll actually would like to drill ice eventually. So that's my answer. One, what we're doing with existing data. The other on what could be a possible mission coming up.
The Blue Origin rocket that just took off and shot 2 satellites to Mars. It's not going to get there for a while. But what is that going to help you at all?
I'm not aware of that. I'm not sure. They are not radar, so
Okay.
Fortunately. I see a question here in the chat about TEM. Okay, from our experience, TEM hasn't been successful in glaciers, but yes, for detecting water ice, for detecting water, it has been used. Actually, my group at University of Arizona, we have been using this drone-based GPR to detect the base of glaciers and stuff, and we have been learning how to operate drone geophysics. The next step actually is to work on our own drone-based GPR and also to create our own drone-based TDEM. So yes, for detecting the water table, I think TDEM is a better option than drone-based GPR. So yeah, that's a great question. And I think probably for water table, TDEM would be a better option than GPR.
Okay. Can you go back to the map of the SWIM map and point out to us where SpaceX is thinking of landing?
So there is an area. It's around, I think it should be, let me see if I can point that out. There are some areas around here, could be like Fligramontes. So it's I think it's around maybe 40 degrees latitude and around 160. There is one of the landing sites there because there are some debris covered glaciers in that area. They are not very steep, and there are many of them. And also, it has been proven the ice could be very shallow. So that could be one of the areas where SpaceX could land. And actually, if you go to the HiRISE website, and if you search for SpaceX candidate landing sites, you will find some high resolution imagery of that as well.
Okay, great. I think it's about time to go to our next speaker. Thank you very much, Roberto, for an excellent talk.
You have just heard a talk in the conference for students, The New Future of Making on Mars. People like you are taking part in the exploration of Mars. You can too. This online conference is sponsored by the Mars Society of Canada and MakerWorks of Ann Arbor, Michigan, and organized by 2 Planet Steel. Please like, subscribe, and watch more conference videos.